Hi, I'm Ryan Baker, and this is Big Data in Education. In this video, we're going to talk about transfer learning and active learning. A lot of times we build a model. We want it to work in other contexts, and we've talked a lot about that already in this week and the previous week. Transfer learning is where we more explicitly go beyond just doing that, just saying we're going to take our model and use it in new contexts and hope, based on good evidence, it works. We're actually going to say, can we go beyond that to actually make our model better for a new task? So can we apply the knowledge gained from one task to another task? Most commonly, this consists of building a classifier or a regressor in one context and then finding a way to use that classifier in another context, possibly with some mods. There are a lot of transfer learning strategies. One of them, very popular these days, is pre-training, where we build the model on a huge general data set and then we use fine-tuning, we talked about that last video, to adapt to specific problems. Pre-training requires some new data, but it's very effective on language data these days, and there are examples of this in education. It's only occasionally useful for interaction data, but there have been successful examples. See Swami et al.'s work in 2020. A second big approach is feature extraction, where we auto-generate features in an original dataset using, for example, an autoencoder, and then we apply those features in a new dataset. And Emerson et al. Show an example of that in education. This requires both the old data and the new data. A third broad transfer learning strategy is domain adaptation, where we adapt or refit the original model for the new domain. And this might not require new data at all, which makes it a very powerful strategy for cases where we have to do something in a new context. Some of the domain adaptation strategies include, first of all, feature alignment, where we conduct regularization, so things like unitization or other ways of kind of casting a feature's values to a common scale. So we use regularization or other transformation on features to make them more directly mappable between domains. See, for example, Nguyen et al. Let me give an example. Let's say you're trying to predict who's going to get good grades in college, and you've built your model using students who took the SAT test. But now you've got to use the model on students who took the ACT test. Now the SAT and ACT are on completely different scales. You don't want to just take the model as is. But if you could cast both the SAT and the ACT into, say, z-scores, then you might be able to transfer it, especially since those are both normally distributed tests. So that's feature alignment. A second broad category is instance weighting, where we weight cases in the original dataset for relevance or similarity to the new dataset, and then we refit on the original dataset. So in other words, let's say that we're about to apply an affect detector in rural schools, and our original model has urban students, rural students, and suburban students. We might try weighting up the rural cases in the original dataset and emphasizing those more and see if it'll do better on our new data. A third category is adversarial training. In adversarial training, we train an adversarial model that can distinguish the domains along with the main classifier. So we're both training on the thing we want to classify, and we're trying to classify which domain the dataset is in. The main classifier is rewarded for performing well on the main task and for the adversarial model performing poorly. And this results in models often that will work well on both domains. So that's transfer learning. Active learning is the related problem where a machine learning algorithm identifies what it doesn't know and asks for assistance. Wouldn't that be great if machine learning could do that? Wouldn't it be great if all of us could do that? The prototypical situation for active learning is we have a partially trained machine learning model. There's no more labeled data. We're out of labeled data for the moment. But we've got a pool of unlabeled data. And the algorithm is now allowed to ask for a data point to be labeled and receive it. It's too expensive to label all of it. It's too time-consuming to label it randomly. But goodness, if we could just pick a few of the right ones, maybe we could make our model a lot better. And the question becomes, which data point should the algorithm ask for? There's a few options. One of those options is the data point we're most uncertain about. It's the data point that we just are closest to a 50-50 on. We just don't know what the answer is. Maybe it's the most informative data point. You might think that sounds really similar to the most uncertain, but the most informative data point is the data point which information about would most change the model's probability distribution of predictions. So, whereas uncertain is, this is a data point I just don't know about, informative is the one that gives me the most new information. And Something, again, slightly different than most informative is most impactful. The most impactful data point is the data point that would most change the model itself. So we have, do we want to look at the data point we most are uncertain about? We have the least information about this data point. Do we want to look at the data point that if we knew the answer would most change the predictions we're making? Or do we want to look for the most impactful data point, the data point that would most change the model itself? And those are our alternatives. Now, 2 slides ago, you were probably asking, Ryan, why did you suddenly start talking about active learning? What does that have to do with transfer learning? And the answer is because one of the best approaches to transfer learning is active learning. If we want to transfer a model from domain X to Y, one of the ways to do it is to take that model and then label a small number of data points in domain Y to improve the model for domain Y. And it's active learning that we use to choose which data points we should label within domain Y. People sometimes call this the warm start method, as a contrast to the cold start of having a new domain and not having much for your model to decide on. In this case, the warm start is we start with a model that's already, we think, better than nothing, and we use active learning to improve that model for the new domain. An example of this in education is seen in work by Shamya Karumbaya and her colleagues. They took a large data set of affect labels from one population, and they used it as a starting point for an affect detector for a second population. They used active learning to add training labels from that second population, and then they looked at how it did. And they found that it actually wasn't beneficial in every case, but it led to better performance on the new population in most of the cases they looked at. Now, another method that's related to active learning, but not quite the same, is mixed initiative learning. In mixed initiative learning, the user can choose which data point to label next, or the system can propose which data point to label next. And the user gets to pick which of these is going to happen. Also, in mixed initiative learning, the user can choose the labels or categories that it's selecting from in the model, or the system can use unsupervised methods to propose categories, and then the user can iterate on those. And an example of both of these is seen in the combination of Cody and Encoder by Jae-yoon Choi and her colleagues. It's a really cool system, and people in the quantitative ethnography community are using it more and more. A related approach is called learning and deferral. In learning and deferral, for a real-world task, you use the model output when it's high confidence. But if it's not high confidence, the human being is asked to make the decision or the label. An example of this is seen in Lee et al. 2023 for short answer grading, where if the model is uncertain, the teacher is asked to provide the grade. So to sum up, transfer learning, active learning, and mixed initiative learning. These are essential contemporary methods for making classifiers general across contexts and efficient to transfer and develop. This is really important because ultimately, we don't want to have to build an entirely new model for every single case. We want to be able to say, okay, we've learned from these related cases, now can we do something here? And then active learning is something we can use to help us build forward and warm start. So that ends week 3, and we're about to have a big shift in the course. For these first 3 weeks, we've been talking about prediction models in their various forms and manifestations. Now we're going to shift to kind of the rest of the course, where we talk about all the other great things you can do in educational data mining. And we're going to start that with knowledge tracing, the second widest application of data mining machine learning in education. I'm Ryan Baker, and I will see you next week for that continuation. Thank you very much.